Mr. Drew, let me talk to you for a few minutes about inverse trig functions. Now, your textbook has these restrictions about, what can you get from inverse sine and inverse cosine and inverse tangent. And the book will tell you that inverse sine of x, when working with it as a function, will only be able to give you answers, or they'll only accept answers between negative pi over 2 and positive pi over 2. Inverse cosine of x, again, as a function, can only give you answers between 0 and pi. And then finally, inverse tangent can only give you answers of negative pi over 2 and positive pi over 2. Now remember, what do you put into a trig function? You put in an angle measure, and what you get out are the sides of a triangle. Well, these are all inverse trig functions. So you're not putting in an angle measure, you're putting in the sides of the triangle. You're putting in the y over r, or the x over r, or the y over x, and then finding out what the angle measures are from those ratios. So when sine is y over r, you can't have values that are outside the range of negative 1 and 1, or in this case with the inverse function, the domain. You can only plug in values between negative 1 and 1 because, well, like say, what's the sine of 30 degrees? 1/2. What's the sine of 60 degrees? Square root of 3 over 2. What's the sine of 90 degrees? Or pi over 2. That's the largest value for sine, where you rotate pi over 2 radians or 90 degrees. The largest value you can get from a sine function is 1. If you go around to 3 pi over 2, or if you go around to 270 degrees, the lowest value, the smallest value of sine you're going to get is negative 1. So on the inverse trig function, where you're plugging in those ratios, you can only plug in values between negative 1 and 1. Same with cosine. Cosine and cosine really are exactly the same shape. There's just a phase shift between those two graphs. And the tangent graph goes up and down forever, so you can plug any value you want into the inverse tangent function, but you'll only get answers between negative pi over 2 and positive pi over 2. And just try it with your calculator. Put it in degree mode and find the sine of 150 degrees. Now we know it's 0.5 if you know the unit circle, but just try it with your calculator. Now do the inverse sine, second sine of what that answer was that you just got, which was 0.5. The calculator is not going to give you 150 again, or, well, you can put 5 pi over 6 in, but that decimal might be kind of weird to look at. It'll give you 30 degrees. Now why is that? That's because calculators and computers basically can only work with functions. They cannot work with relations, okay? So here's a graph of y equals the sine of x. We're talking about inverse functions. Now, do you remember how to graph an inverse function, or if given a graph, how to sketch the inverse function? This blue line might be a tip. When you graphically when you take a graph and you try and sketch its inverse, you take the x and the y variables and you flip them, or you reflect it around the line y equals x, right? Algebraically, if you want to find an inverse function, you take the x and the y variables and you switch them and you resolve it for y. So, geometrically, that's the reflection over the line y equals x. So this sine graph reflected over the line y equals x, so I can look at the inverse graph, is going to look, this is going to be a sketch, but it's going to look something like this. So this blue line is y equals the inverse sine of x. Well, let's talk about, the sine of, think of the unit circle. Where is sine equal to 1/2? It's equal to 1, I'm going to do this in degrees. It's equal to 1/2 at 30 degrees, and it's equal to 1/2 at 150 degrees, or pi over 6 and 5 pi over 6. And then you can rotate around the circle again and have it at what? 30 plus 360 is 390. And then 150 plus 360 is 360, 460, 510. And you can rotate it around again, but I don't keep trying to add 360 in my head. You can also, of course, go backwards. So as you cycle around that unit circle over and over and over again, there's going to be a ton of places where sine is equal to 1/2. So when you ask for the inverse sine of 1/2, there's potentially an infinite number of possibilities because you could just keep spinning around that unit circle. So we can't have that. A calculator cannot run indefinitely just because you ask it to do inverse sine of 1/2. No, it's just going to give you one answer, and it's going to be 30 degrees or pi over 6. Now, what's happening here is when you have a graph and you want the inverse of that graph, or when you have a function and you want the inverse of that function, and you want an inverse function, not an inverse relation, the original graph needs to be 1 to 1. It needs to pass a vertical line test and a horizontal line test. Well, this sine graph is oscillating along the x-axis, and therefore it will certainly not pass the horizontal line test. So what we do, and where these restrictions come from, is we take the sine graph and we restrict its domain to basically just this tiny little scribble, scribble? Is that even a word? This tiny little S-shaped curve between negative pi over 2 and positive pi over 2. And now this little white line would pass the vertical test and the horizontal test. So this sine function restricted between negative pi over 2 and positive pi over 2 is now acting as a 1-to-1 function. And so now let's take this little white line and reflect it around the line y equals x. And of course, if we erase all the original domain of y equals sine of x, then we have to lose all of this reflected graph. And what do we get? We get a little blue squiggle that goes from negative pi over 2 to positive pi over 2. Well, there you go. Now, these marks were on the x-axis originally. When we're talking about an inverse function, those x's become your y's. So the bottom of this blue graph as an inverse is negative pi over 2, and the largest answer you can get from the blue graph, the largest range value, is positive pi over 2. Now, I'm not going to do this kind of sketching for every single trig function. That'll be in your textbook. But that's sort of just explaining how we take these trig functions that oscillate or have a series of periods or an indefinite number of periods along the x-axis. We find the inverse, which means that now runs up and down the y-axis, and we sort of just basically erase a lot of those range values and restrict these answers to inverse sine as a function are only going to give you values of negative pi over 2 to positive pi over 2, this little blue squiggle. Inverse cosine, 0 to pi. Inverse tangent, negative pi over 2 to positive pi over 2. These restricted range values are all you're going to be able to get out of your calculator when you ask it to do an inverse trig function. So let's say that, again with your calculator idea and the unit circle, you say, well, what is the sine of 225 degrees? The sine of 225 degrees is going to be negative square root of 2 over 2. If you ask the calculator to the inverse sine of negative square root of 2 over 2, it's going to tell you it's negative 45 degrees. Now, what does 225 have in common with negative 45 degrees? They're both 45 degrees off of the x-axis. They both have the same reference angle. So your calculator may very well give you a usable angle measure, but not necessarily the one that you may be looking for. If you want an angle in quadrant 3, your calculator will not be able to tell you that. It'll give you another angle that has the same reference angle, and you need to figure out the right answer. Okay, let's actually write a couple of examples down. What is the inverse sine of negative square root of 3 over 2? Well, if you know your unit circle really, really good, you might know that that is going to be at 4 pi over 3 and 5 pi over 3, and those are kind of like correct answers, but not if we're forcing inverse sine to act as a function. If you type inverse sine of negative square root of 3 over 2 into your calculator, or if you work with this as a function, your calculator would tell you that the answer was negative pi over 3 or negative 60 degrees if you have it in degree mode. So while these are sort of correct on the unit circle, these angles will give you a sine value of negative square root of 3 over 2. they're not within the restricted range of inverse sine when it's acting as a function, okay? So let's take a look at the inverse cosine of negative square root of 2 over 2. Well, on the unit circle, if you're just thinking of that, the cosine is equal to negative square root of 2 over 2 at 1, 2, 3 pi over 4. And then 1, 2, 3, 4 pi over 4, 5 pi over 4. But the only one of these answers that are within the restricted range of inverse cosine when it's being worked with as a function, what your calculator will be able to give you is 3 pi over 4, 135 degrees. Let's take a look at the inverse sine of the sine of 5 pi over 6. Now remember, you put angle measures into trig functions and you put in the sides of a triangle, the ratios x over r, y over r, whatever, into your inverse trig functions. So the sine of 5 pi over 6 is again 1/2. And the inverse sine of 1/2, while on the unit circle, you do get a sine value of 1/2 at 5 pi over 6. But if you're working with it as an inverse function, you can only give me an answer between negative pi over 2 and positive pi over 2. So the inverse sine of 1/2, the only acceptable answer as an inverse sine function is pi over 6. So we started with an angle that we didn't actually really get back to. Your textbook will have inverse properties as well, and it'll explain, you might want to memorize them to show you like when these inverse trig functions just simply cancel out. But when you're given answers or angles that are on the unit circle, I like to just sort of think my way through the problem instead, using just these restrictions to figure it out. Okie dokie, let's just keep doing some examples until I run out of time. I might need to make a second part to this video. We'll see when my alarm starts going off. The tangent of the inverse sine of 5 over 13. Okay, now, you have been actually given this problem and done this question probably before in your trig book or your pre-calculus book. You've done these kind of questions before, it just looked different. So let's get this set up anyway. Again, what do you put into an inverse trig function? The sides of a triangle. This is a positive ratio, and therefore you can either be in negative pi over 2 or positive pi over 2. So sine's positive in quadrant 1, so you want to draw your angle in quadrant 1 between 0 and pi over 2. So we're going to get this thing set up. And I hear my alarm going off, so I'm only going to get this one example done, so there will be a second part. We draw a reference triangle. Sine is y over r, so it's going to be 5, 13. The Pythagorean theorem, a squared plus b squared equals c squared, will tell you that this third unknown side is going to be 12. You probably have to work that out with some of your questions. And once you get your reference triangle set up, you're ready to set up any trig function you like. This is similar to the questions earlier where I said the sine of theta is equal to blank, what's the cosine of theta? Or the sine of theta equals 5/13. What do you get from an inverse trig function? An angle measure? What is the tangent of theta? Yeah, that's y over x. That's 5 over 12. I'm Mr. True. Bam! Check out part 2. I got it. Bam, Mr. True. In part 2 of evaluating inverse trig functions, we're going to, as you can see with our 3 examples I'm about to work with, do some problems that don't actually have any angle measures. Don't have enough information to find any concrete numerical values. We're just going to be setting up our triangles in the appropriate quadrant and then setting up angles and finding ratios. So let's see here. In a trig function, you put in an angle measure. With an inverse trig function, you're putting in the sides of a triangle and getting out an angle measure. So we're going to work our way inside these parentheses all the way and out of them and see what we get. So the inverse sine of x. Well, since this is an inverse sine function, we must be putting in the sides of a triangle. So I'm going to draw an angle in quadrant 1, or just draw an angle theta. I don't know what its angle measure is, and I'm not going to be able to find it because I don't even know, really what my numerical values are. I just have, this value of x. Well, if this is an inverse trig function, let's remember that this is the side of a triangle. So remember that sine is either y over r, but saying that might be confusing since this isn't, this x value. So let's remember that sine is opposite over hypotenuse. So if this is angle theta, and if it's an inverse trig function, it needs to be between either positive 90 and negative 90. I'm going to draw these in quadrant 1 anyway. So we have this measurement of theta, and sine is opposite, so x over hypotenuse of 1. Remember that's SOHCAHTOA, right? Sine's opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So if we're going to set up the tangent function, because remember, from an inverse trig function, we get an angle measure. That's why I'm setting up this triangle, so I can set up, not find theta, but at least set up its right triangle. So we're going to work out Pythagorean theorem because we're missing a side of a right triangle. So let's say a squared plus b squared equals c squared. So that's 1. Well, let's just put the square there for good measure. So we're trying to find this length. It's one of the legs, which I've identified temporarily as a. So we're going to have 1 squared is 1, and I'm going to move the x squared over with subtraction. So a squared is equal to 1 minus x squared, which means a is the square root of 1 minus x squared. Well, now that I have all 3 sides of my triangle set up from the inverse trig function, now I can just say, well, what is the tangent of theta? Well, tangent of theta is, from SOHCAHTOA, opposite over adjacent. So from theta, it's y over x, but I'm not going to use those that language because we're just using the variable of x. So opposite over adjacent, so the tangent of theta is going to be x over the square root of 1 minus x squared. And if we're making sure that we do not leave any radicals in the denominator, we're going to multiply top and bottom by 1 minus x squared to rationalize the denominator and get a final answer of x times the square root of 1 minus x squared over 1 minus x squared. And these x's do not cancel out because you cannot cancel out just part of a term when you have basically a binomial here. This is 1 minus x squared. You cannot cancel terms. So these x's will not in any way cancel out. And that's our final answer for the tangent of the inverse sine of x. So let's take a look at our next example. These are all going to be very, very similar. I'm just going to be practicing our Pythagorean theorem basically to fill up the missing sides of these triangles. We got cosine of the inverse sine of 2x. So remember, if this is inverse sine, this must be the sides of a triangle, and from it we are going to get an angle measure. So we have to set up that angle measure. Well, from this we get theta, so let's draw theta out. So there's theta. If this 2x is going into the inverse sine function, that must be, again, opposite over adjacent. So from theta, we have an opposing side of 2x. The hypotenuse, again, for this is going to be 1. And our missing side down here, this is really pretty much very, very similar to our last example, is going to be, well, let's call that a, so I can call it something. A squared plus b squared equals c squared. So we have a squared plus 2 squared is 4, x squared equals 1. We're trying to find out what a is, this adjacent side, so we're going to move the 4x squared over with subtraction. A squared equals 1 minus 4x squared. We're going to get the power of 2 away from a by square rooting, and a is equal to the square root of 1 minus 4x squared. Now, my students, a lot of times, unfortunately, like to, they might like to say that this is 1 minus 2x. The square root of 4 is 2. The square root of x squared is x. The square root of 1 is 1. But saying that this was equal to 1 minus 2 would be like you trying to say that the square root of 4 plus 9 is equal to 2 plus 3, and that is not equal to 5, because the square root of 13 we know has got to be less than 4. So certainly it's not going to equal 5. So please, when you have two perfect squares inside of a square root symbol, don't think that you can cancel those out or actually square root each term individually. That does not work. So now that we have our right triangle all filled up, and we have theta set up in this right triangle, what is the cosine of theta? Well, cosine of theta is equal to the adjacent side. So next to theta, the adjacent side is square root of 1 minus 4x squared over the hypotenuse of 1. So the cosine of theta is 1 minus 4x squared. For our last example, we have the inverse cosecant, or excuse me, the cosecant of the inverse cosine of x over the square root of x squared plus 9. So again, if this is an inverse trig function, this must be the sides of a triangle, and we're going to get out an angle measurement. So we have theta. Cosine is adjacent over hypotenuse, so square root of x squared plus 9. Again, SOHCAHTOA. Cosine is adjacent over hypotenuse. Pythagorean theorem is going to help us find that third missing side. So we have x squared plus b squared equals c, which is the square root of x squared plus 9 squared. The squaring and the square root, of course, are going to cancel out. So we have, we have b squared is equal to x squared minus 9, x squared plus 9. And then we're going to bring this x squared over, it's positive, so we're going to bring that over with subtraction, which is going to cancel out those x squared terms. So that means that b squared is equal to 9, and that means that this side that I've labeled as b is equal to 3. So the cosecant of theta, cosecant is a reciprocal of sine, so cosecant is going to be not y over r, but r over y, or hypotenuse over the opposite side. So it's going to be equal to the square root of x squared plus 9 over 3. I'm Mr. Tarut. Bang! Go do your homework.